So today we're going to be looking at web attacks. So this covers a wide range of stuff that was covered in the last few weeks. So we're going to be going over things like cookies, HTTP headers, session hijacking, cross-site scripting, CSRF, access control. We're going to be doing all of that today. There's a lot of topics, but I'm not going to cover all of them in too much detail, just enough detail for us to have like a solid understanding of what's going on with each of them. And if there are any questions about them or you want me to go into more depth into anything, then I'm happy to do that throughout the session or at the end. Just drop them in the chat. Okay, let's get started. Web attacks. Okay, so I'm going to start with a brief introduction of an introduction to the idea of web attacks. Now, before we do that, we all hopefully know what HTTP is, but just a quick recap. HTTP is a protocol, and we use it for web browsing, and it specifies the format or the structure as to how browsers should communicate with servers and vice versa. It's like, this is what the message will look like. You'll have a request and a response and whatnot. Also, something that was covered in the lectures, modern password recommendations. Just this is to do with like authentication authorization, not really related to HTTP. But these were just some things when you're implementing like a website, you want to try and keep these password recommendations in mind. Avoid passwords if possible, quite funnily, like use other methods like biometric or other methods of authenticating people. Don't use rotation unless there's signs of compromise. So that's where, like, you know how we get an email from the uni every few months saying you need to update your password. That's actually bad practice according to industry standards. Recommend secure storage mechanisms, so like storing stuff securely, encrypted, hashing it, salting it, to make sure that even if it is compromised, it can't be easily brute forced or easily broken. Check for weak passwords, having sane password complexity rules. So not things like you need 13 exclamation marks and 14 symbols and 19 letters. Like sane password complexity rules that make it somewhat hard to brute force. Rate limit logins, so you can prevent automated attacks. So if someone does try and brute force, it takes them a lot longer because they have to have some sort of cooldown in place, whether that's IP addresses or MAC addresses or just account cooldowns. And also multi-factor authentication for recovery is something that's highly recommended. So things like 2FA codes, one-time passcodes. I see Hux has just sent a link in the chat as well, passwordstore.org. Yeah, moving on. Cookies. Okay, so the idea of cookies, it's often desirable that we want to keep track of some sort of state or keep track of something on the client side between requests that we don't want to keep sending back into, like, to and from the server. And so cookies let us do this. For an example, we might want to remember the user's preferences. I know a lot of people for their team project had things like accessibility settings. I know our team used cookies and local storage to store things like user preferences, whether they like light mode or dark mode, that kind of stuff that we don't necessarily want to fill the server's database up with, but we might want to store on the user side, on the client side. Cookies allow us to do that. Another example, remembering the currently logged in user. So we might use cookies to store some sort of reference to who the current user is logged in as, like a session ID or a JSON Web Token. However, cookies can also be used to store less desirable things like advertising network tracking IDs, which could be shared between websites, profiling your browsing behavior, and this could compromise privacy. It could lead to your data being like sold off to third parties without your permission, and so cookies can be used for very good reasons, but also for bad reasons. So using cookies to store sensitive data also comes with a risk of theft, because yes, even if this is all done very legally and you're being profiled in a way that is in line with like GDPR, storing that as cookies comes with the risk that if a website's poorly implemented or insecurely implemented, then that sensitive data could be compromised. Or if the browser or the machine itself is compromised, those cookies could be compromised. Another threat is if the cookies are passed in the clear, someone can snoop in on them like a man-in-the-middle attack. If they're passed in the clear between requests to and from the server. Okay, so when we talk about passing cookies and requests, this is usually how it's done. So we can set cookies using special HTTP headers. Remember, HTTP just tells us how we should format our requests to the server and how the server will respond. It's like a language that the two parties speak. So when the server sends a client this set cookie message, all that means is we're telling the client to set this SID cookie to this value. So it's like a dictionary. We have keys and we have values. Key, value, key, value. So the server tells the client to set their session ID to this, the path to this, and secure is kind of like a flag for the cookie, saying this is a secure cookie, and HTTP only means that we shouldn't be able to access this cookie using things like in JavaScript, which we'll explore in a second. But yeah, the server's just saying set these cookies client side. And then when the client responds to the server in a request to the server, it will pass the cookies in the request like this. So it will say, hey server, here's my request, and here's my session ID, and here is the language that I'm using on your website, so don't send me some Russian website back. Moving on. Okay, session hijacking. So web applications often use session IDs as a credential, like we saw on the previous slide. And the idea is this session ID authorizes the user, or it lets the user say, hey look, this is me, I'm not going to log in every time I want to do something on the website, so here's a session ID to prove that it's me. Now, this is great because it means you don't have to send the password every time you want to do something and prove that you are who you say you are. But the idea is if an attacker can get a hold of this session ID, they don't need your password. They're essentially logged into your account on that website. And we talk about this, we describe this as session hijacking. Now, there's a bunch of different ways in which an attacker might steal a session or steal a session ID. And this is including, but not limited to, cross-site scripting, sniffing and interception. So when we talk about sniffing, we talk about like reading the packets, or like a man-in-the-middle attack. Similar to interception, someone's intercepting those packets between you and the server. Calculate / guess / brute force. This is very exhaustive, and if you're using good cryptography, then this shouldn't be as much of a concern. As long as you're hashing properly and you're salting properly, then your password should be secure and protected against this. Or the attacker could grab or set a session ID before the user visits the site. Things like online shopping or cart persistence. This links to cross-site request forgery, which we'll also look at in a later slide. Hopefully that makes sense. If there's any questions, just drop them in the chat. Okay, so in order to defend against session hijacking, there's a few things we can do. This isn't everything we can do, but there are some defenses that web applications can implement. So, and we can also discard session IDs if we think they may have been compromised or anything suspicious happens. So one thing we could do is we could link session IDs to IP addresses. So we can say, okay, if you send a session ID, but you're not 1.2.3.4, then I'm sorry, but we don't think you are Alice, even if you've got the right session ID. So this is good if we have that sort of idea of linking those two together. It prevents those stolen sessions from being seen as valid in some cases. But there are some very big problems with this. If the user's behind a NAT, or network address translation, or a proxy, then it might be hard to confidently say this session ID links to this IP address, and so it might lead to false positives or negatives. ISP proxy pools may mean we need to use subnets, not IPs. So what this means is sometimes your ISP will, if we have a bunch of different networks, your ISP will pool all of those requests together and send it from like a proxy server to different websites. So then the website will think that it's getting requests from the same place when it's actually two different households or two different networks that are sending that request. So that could also lead to false negatives and sessions being falsely flagged as session hijacking when it's really just an ISP proxy pool. And another vulnerability is the subnet may be shared with the attacker. Great, we could link the session ID to the IP address, but if you're in a public cafe and someone, just as Hux has said, if you go to a cafe and connect to their Wi-Fi, your global IP will be the cafe's IP. And so if someone malicious is on the same IP address, even if they've got this link on the server side saying, hey, the session ID is for this IP address, that malicious actor can just log onto the cafe Wi-Fi and use your session ID, and the server won't be able to flag that. So another approach we could take for getting the whole IP address thing is we could link the session ID to HTTP headers, like the user agent header. But this is also very outdated. This can be trivially faked because we can just modify what we're sending in the HTTP request, and this can usually be guessed or captured. For example, if we trick the victim into visiting a malicious site, we can do things like cross-site request forgery, or we can see what they're passing in their headers, like their user agent headers, to try and mimic their requests on another website and replay those requests. Okay, so I'm going to move on to cross-site scripting now. We're going to look at what it is and how we can defend against it. So cross-site scripting is when we inject client-side code into web pages which are viewed by other users. Now, the attacker tricks the web app into thinking, or into including some malicious code which isn't intended to be there by the developer of the website. So the motive of an attacker could spread widely when carrying out this kind of attack. So they might want to display images, open pop-ups, change page contents, or hijack the session. They can do a lot more than this. They basically have control over any client-side code which executes for clients. So they could do anything malicious. This is probably the most malicious out of these four in this case, or changing page contents, but the possibilities are endless. So the underlying issue, which allows this XSS to be exploited, is poor input-output validation. And this is a big rule, which I know Danny also touched on in the earlier session. Never trust a user's input. Imagine every user is out to get you. Do not trust anyone. You've got to be very, very schizophrenic as a developer. So there's two types of cross-site scripting. We have stored cross-site scripting. This is where the attacker can inject malicious code into server-side storage, for example, a database, and that code is later on displayed to other users. So, for example, if we have a comments page on a website and it doesn't properly sanitize inputs and outputs, I might be able to comment something like script tag console.log, Texie was here, close script tag, no comment. And in a good website which sanitizes inputs, it should just show this as my comment, or maybe just not allow me to comment that. But in a website that's vulnerable to cross-site scripting because it's not properly sanitized as inputs, it might render it as an actual HTML script tag, logging Texie was here in the console for anyone who views the comment. So the idea is you want to avoid this, and the way you do that is by sanitizing inputs and outputs. Another type of XSS we have, so we've looked at stored XSS, we also have reflected cross-site scripting. This is where injected malicious code isn't stored on the server, but it's immediately displayed on the visible page, or on the visited page. So, say we had a website like this, mymanpages/manpage.php, question mark title equals that, and program equals GCC. So we might have this PHP page that dynamically renders the HTML, embedding the title directly like this with no input sanitization whatsoever. Then an attacker could use this with a malicious input. They could put and title equals script tag, malicious script, close script tag, and program equals GCC. And this will just basically in here put that code straight in here. And so whenever a user visits this site, it instantly runs that script, which might steal a cookie. So that's something we want to also avoid. Okay, moving on. So to defend against cross-site scripting, as I mentioned, we can validate the user input. So we only allow a very strict subset of inputs. So if someone tries to comment a triangle bracket h1 hi /h1, input validation would basically say, don't allow this. Don't even allow users to type this in, right? But then we also have output filtering, which is another approach we can take, where when we display the output to the end user, we use things like HTML encoding. This is where we actually store this triangle bracket as the HTML equivalent for that character. And that means it actually renders as the string, this tag. It doesn't try and render it as HTML. Or we can use marked up output. We can use a domain specific language. Hopefully you guys are familiar with Markdown, so that's where we use a dedicated syntax and we convert Markdown, for example, into a safe subset of HTML where we maybe only allow h1, h2, p, ul tags. Maybe we only allow those tags. Any other tags in HTML we automatically deny. So the idea is we can either control what the user can feed into the database or into the website, or we control what we're then outputting back to users. So this is like defending. This is defense from malicious actors, and this is more like protection for potential victims. Hopefully that makes sense. We've got a message in chat. Figured out what accessible only on that path means. When you send a HTTP response from the server, you can add a set cookie header to tell the client's browser to set the cookie. If you provide a path as part of this header, the server will only send the cookie header if the path of the request matches the path of the cookie, I think. Yeah, that sounds about right. I'll search it up as well at the end as well, though, just to confirm. Okay, but yeah, this is how you can defend against cross-site scripting. Other things you can do, you can enable HTTP only cookies. So I'm not sure if any of us remember, but back here we set this cookie to HTTP only. We gave it this HTTP only flag. And what that basically does is it means we can't access those cookies via JavaScript. So even if we did have something like some sort of cross-site scripting which tries to access document.cookie, as we saw on that example which I did on the website, we won't be able to access the cookie with this. It's not accessible via JS. HTTP only means we only send it into the we only send the HTTP cookies in the HTTP requests. We cannot access it through JavaScript or through like script tags. We can also enable content security policies. So a content security policy can do things like preventing inline scripts, and it limits which domains can be requested. So we can't do things like script source equals texie.land/safe.js. We can't do something like this if our content security policy doesn't allow us to fetch scripts from texie.land's domain. We might only allow from the same domain or from like a certain subset of domains. Broken access control. Okay, so the category of broken access control includes cases where the attacker can act outside of their intended permissions. So object references, like a path traversal, with a link like this, myblog.org/index.php !entry equals /etc/password. This could allow remote access to any file on the system. If this entry parameter basically just reads the file and feeds out the contents, then we can access any file on the system. So we want to avoid this, right? We want filters to be put in place, and we want internal web server configurations and external OS permission configurations to be added so we can limit the impact of this vulnerability. So internal web server configurations, that's basically saying when we get a request in, maybe have some sort of middleware to check that the paths that the user's feeding in are valid. This was an issue with Sensible Furniture where you could access I believe it was the etc shadow file, which you shouldn't have been able to access. If the web server had protection in place saying only allow access to things in this folder, then that may have prevented that. But then we also have OS permission configuration. So this is external configurations where the operating system says, okay, only this user can access these files, only this user can access these files. So when we talk about OS permission configurations, imagine this massive box is, okay, imagine this is our system, and our system has two users. So we have, okay, maybe we have our root user, and then we also have John. Okay, imagine one of our users is John. Now, if our entire web server is hosted in John's user account, and we have a file maybe in the root, like etc/shadow, this is an example of external configurations where John cannot access this file. So the web server running inside John's account won't be able to access this file because this file's permissions only allow root to read and write it. So that's an example of external configurations. Yeah. Okay, moving on. Form validation. Now, validation of form inputs is also something you want to configure. We don't want to just do these validations on the front end. We should do those checks in the server too. So if we have a website where you have to be 18 plus, for example, to use it, on the front end it's all great saying if age is less than 18 then error, but in the back end, like the user can manipulate the front end, right? Think back to trust no one, right? The user can just ignore this check, or they can manually send a request using something like curl to the server. So the server should also have this check, right? The server should also validate the inputs that the user's sending in, because in theory the user has control over everything up to this point. It's not like they have control up to this point. They have control over everything before the request actually hits the server. So you want to verify everything server side as well. Integrity. Okay, if we want to ensure information stays unmodified in like things like forms, we can add a MAC, a message authentication code, which we construct with a server-side secret key, and we send within form data. This isn't as much of an issue now because we don't use outdated tech stacks, and we don't use things like PHP for many websites anymore. For like startups at least, it's not really used in industry. But we can have MACs which keep form fields like integrity in check. I'd say how this relates to modern technologies most is with JSON Web Tokens. So with JSON Web Tokens, we have a server-side secret, and we need that secret in order to create these JSON Web Tokens, or in order to generate them. And so if someone tries to forge their own JSON Web Token, they won't be able to compute the signature because they need that server-side secret key in order to compute that. Right. Moving on. CSRF. Okay, so cross-site request forgery is where we exploit the browser's trust relationship with a website. For example, if a user's already logged into a website, the browser sort of trusts that website to an extent. So the attacker can then trigger some sort of malicious action by getting the user to open a malicious link going to a bad website, and that triggers the browser to take some action on the target site on behalf of an authorized user. So I've got an example here. Let's say we have a website, bank.com, right? Imagine the user has already logged into bank.com. And so there's this page, which is like bank.com/pay, okay? And it's a post form, which takes in two things. It takes in how much you want to send and who you want to send it to. This is the only thing you need. The browser already has like the cookies and stuff stored. You're already logged in to this bank website. Now let's imagine someone wants some free Robux, and they hear that you can get free Robux at freerobux.techsy.land, right? They go to this website, enter your Roblox name, and they type their Roblox username, and they press this go button. Now, an example of CSRF in action is where this go button basically triggers, it actually sends a request to this URL. It posts to this URL, and it fills in the amount and the recipient as these two values here. They're just hidden fields. They're part of this HTML form, but they have the hidden attribute, so you can't see them, or the user who's trying to get their free Robux can't see those hidden fields. So when this request is sent to the server's like, okay, I mean, we trust the user because they've already logged into this site. This is the amount, and this is who we need to send it to. Let's just take 1,000 out of their account and send it to SBF, right? In this case. But the idea is the browser already has that trust relationship with bank.com. So when someone goes to this website and fills in the form, it actually triggers a completely different thing, right? Something that the user was not expecting at all, right? They were expecting their Robux, but instead they got £1,000 ripped out of their account. I mean, the website might also give them free Robux, you know, just to like mask the fact that this is going on. Just take it longer for them to notice this. But no free Robux for now. Yeah, sorry, but that's an example of cross-site request forgery. Now, to avoid this, we can have something like this, right? So we generate a nonce, or like a randomly generated hard to guess value. The bank generates this and sends it to the user when they like first log in. To answer your question, Witty, yeah. So the user would already be logged into bank.com. The idea is they already have that trust relationship with bank.com before they try and get their free Robux. So this nonce, the server basically sends it to the user when they log in. So then if this free Robux site tries to send this request, it's missing this nonce attribute, right? So the server will reject it. It will be like, hey, no, what's the magic word, right? So the idea is this website cannot predict that nonce because only the user on the correct website can get that nonce from the server. So it provides that extra security, and it makes it harder, if not impossible, for another website to try and mimic that request and abuse that trust relationship. So we can prevent CSRF by having that double cookie trick. So that's what I actually know. So yeah, we can have CSRF tokens. So that's where we generate a nonce for each session, and then we send that in the post request and check server side. I believe these two are pretty much the same. It just depends on how you implement it, but the idea is you want to have that check in place. But we can also avoid GET requests for any sensitive state changes, or we can use a framework that has built-in protection. A lot of modern libraries and frameworks will have protections against cross-site request forgery. Right, now I want to move on to content security policies, because we've discussed these briefly, but I'm going to go into what the differences are between them and which ones we have that we could use. Okay, so we have the same origin policy. This is a standard browser-side mechanism where we protect simultaneously running web applications from one another. It restricts access to the document object model, so that's all the HTML code and rendered elements on the page. APIs for web access using things like XML HTTP request or fetch. It restricts access to cookies, HTML5 local storage APIs, cookies and HTML5 local storage APIs to pages from the same domain. So like on the same protocol, host, and port. So the same origin policy is just a set of rules which says you shouldn't be able to access stuff that is from like any other domain. You should only be able to access stuff that's on the same protocol, same host, and same port. So if we have something like localhost :3000, it should only be able to access resources from localhost :3000, maybe slash public / logo.png. It should not be able to access texty.land / robots.txt, because the same origin policy only allows this request to go through. It doesn't allow this request to go through. I'm sure many of us have come across thousands of no access control origin errors trying to spin up some like React page or something. They are horrible, but can usually be fixed by just like loosening the policy, which I'll get into. So with the same origin policy, browser sandboxing also enhances this. In most modern browsers, different tabs or different frames run in different processes. So that means that they don't sort of interact with each other. It's a lot harder for cross-site scripting and cross-site request forgery if everything's running in separate, isolated processes. Then we have cross-origin resource sharing. So this is a slightly more relaxed version compared to same origin policy. So with course, we want to allow servers to specify permitted origins using special HTTP headers. So same origin restricts JavaScript from making requests to other origins, but this is often very restrictive. If we want to, for example, communicate with OpenAI's GPT API, we can't do that with the same origin policy, right? Because it's on a different domain. So cross-origin lets us specifically say, okay, allow requests to this website as well. And this might be like OpenAI's root API URL. And this is just a HTTP header. Same way we have things like set cookie as HTTP headers. This is also a HTTP header, which we can pass into clients, which allow us to get resources from specific domains. Okay, that's everything I wanted to cover. Are there any questions in chat? Okay, I'm going to end the video here. If you have any questions, drop them in the comments, like, sub. See you soon.